We've tried a couple of different estimator objects now, but neither of these really gave us the performance that we were looking for. With both of the estimators, that is both the linear regressor and the DNN regressor, with the small training dataset that we had in memory on our virtual machine, we got root mean square errors greater than we obtained with our really crude distance based model. So clearly, something isn't really working for us. But that's fine because we are going to start introducing some pretty serious refinements. Let's start by clicking on part C, that is the batched IPython notebook. As the comments tell us, we are going to introduce two small but significant changes to our model. For one, we are going to refactor our code so that we read in the data from files, that is, from a large number of data files potentially in a cloud storage bucket. And the second, we are going to change our features, that is the x variables, so that we have the ability to transform those variables before we input them into our model. So let's get started, and first let's understand how we are going to refactor the input. Recall that with an estimator object, we train that object using the fit method. The fit method needs to be given an input function. That input function will take in a data frame consisting of the training data, and it will return a pair. The first element in the pair is going to be a dictionary of the features. The second element in the pair is going to be a label list. Now we cannot change the basic structure of this make input function, but we can change it in one important way. Previously, we were reading our input data directly into pandas data frames and passing those on. This meant that by definition, the size of the training data was pretty small. We are now going to refactor our code so that we can read these in from files which are in disk. These will then be a lot larger potentially than the pandas data frame that we just went with. So let's start refactoring the input. As before, we introduce some helper variables. The first of these is called CSV columns, and it's simply a list with the names of all of the columns in our CSV data. The second is the label column, which here is called fair amount. Again, nothing too surprising there. The third is a little more interesting. This is a list of lists. Notice how this variable, which is called defaults, has one default value for each of the input columns. And each of those default values is a list in and of itself. So defaults is a list of lists. Okay, let's now recode our make input function and replace it with a new function called read dataset, which will do everything that we just said it would. As before, this has a file name that it takes in, but it also takes in the number of epochs, the batch size, as well as the mode. So it takes in more variables than the previous make input function that we had. Within our function object, the first item on the agenda is to create a list of all the input files. For now, we are just going to read in the simple small files that we previously had, but later we'll see how this can be used in order to match, using regular expressions, the sharded files which are output by data flow. So this input file names variable is a list of all of the files that match a particular pattern. That pattern could include a regular expression, and in this way we can match a sharded large number of files such as the output of Spark or Dataflow. In order to create this list of input file names, we make use of a utility function provided by TensorFlow, that is the tf.train.match file names once method. We then go ahead and create a queue. That's a queue of file names. That again makes use of another utility method, that is the string input producer. The string input producer method is going to create a queue, that is a parallelizable data structure. In this queue, we will have all of the input file names repeated for every epoch that we wish to specify. So for instance, if we have two input file names and the number of epochs is equal to 100, our file name queue will have 200 elements. That is, each of the two file names repeated 100 times. This is a way of making sure that each of the files in our input training data is going to be repeated as many times as we specify in the number of epochs. Notice also that we set shuffle is equal to true. This is in order to make sure that the elements or the rows in those file names are read in random order. And this eliminates the possibility of bias happen to be introduced because of the order of the rows in the data. Once that's done, we go ahead and make use of the text line reader. This is a utility object provided by TensorFlow, and we invoke the read up to method of this text line reader. Given a queue of file names and a batch size, the read up to method is going to read data in batches. It will return a pair. The first element in the pair is the number of records read. We aren't interested in that, so we just ignore it using the placeholder. The second value, however, in the return value is indeed important to us. This is now going to be a data frame consisting of all of the rows that were read in. This batch of data is contained in the variable called value. Let's go ahead and invoke the tf.expanddims method on value. We call tf.expanddims -1. This will add one additional dimension at the very end of the data that we have, and the result of that will be to convert a list into a list of lists. We've encountered tf.expanddims a bunch of times so far, so hopefully this makes sense. We are almost done with our refactoring of the input. All that's left for us to do is to now invoke the tf.decodeCSV method on this value column's tensor. That will have the effect of returning one tensor per column. In a sense, this is changing the orientation of our data from horizontal to vertical. We then get a dictionary with all of the features exactly as we'd like, that is, with the keys being the feature names and the values being the feature columns. We do so by zipping the names of our CSV columns along with the tensors that we just obtained. After we invoke the zip method, we convert these into a dictionary that's called features. We pop out the label column from this because, of course, we do not want to pass in the y variable as one of the x's. That would defeat the whole purpose of building this model. We now have the features as well as the label, and so we are in a position to return a pair. This is the features comma label pair, which is of course required by our estimator object. Once we have this read dataset method in place, we can go ahead and invoke it three times for the training data, the validation data, and the test data. Notice how when we invoke it with the training data, we specify the mode is train. For validation and testing, the mode is equal to eval. This is not something that we need to make use of directly, but it might be significant for the estimator. For instance, dropout is applied only during training, not during testing or evaluation. In any case, we are now done refactoring our input. So that's a great start. The next item on the agenda is to refactor the manner in which our features are created. Remember that this is simply changing how we pass in the list of columns into the instantiation of the estimator object. This for now is really easy for us to do. We simply create a list of input columns where we have one real valued column for each of the feature variables. That's the pickup longitude and latitude, the drop off longitude and latitude, and the number of passengers. That's really it for now. We can now go ahead and create and train the model exactly as before. Once that's done, we can also evaluate it on the validation data. We do so and we find that the RMSE is now somewhat better. It stands at about 9.7. So that's still a lot worse than our crude benchmark, but it is better than what we just obtained a moment ago.